So today we have the first in ASA ECR Symposium series. Our first speaker is Samuel. He's worked and studied in Hong Kong, UK, and US, so a lot of places. And at the moment, he's at ANU doing his PhD on high-redshift quasars and looking at them with multi-wavelength observational data. So if you'd like to start whenever you'd like to start, Samuel, go ahead.
Sure. It's really great to meet all of you and see the community at University of Queensland. And it definitely seems a lot more tight-knit than it is here at ANU. I feel like that's something we need to change. But anyway, let me get started with the share screen. Then hopefully you can all hear me clearly.
Yep, sure.
Yeah. Then let's see here. Right, so it's my pleasure to be presenting a talk here about my work for the University of Queensland as part of the ASA ECR Symposium series. So I would have preferred to deliver this talk in person and meet all of you in person, but for today we'll have to settle with an online presentation. I will, however, stick around after the talk for any further questions and discussion. And of course, my email is always available as well. So I'm Samuel Lai, as previously introduced. I'm fairly well traveled, having studied in the United States, in the UK, and now in Australia, and growing up in Hong Kong. I'm currently a final year PhD candidate at Australian National University, and I work on these ultraluminous high-redshift quasars. Alongside a wonderful research group, Chris Wolf is here today on the call. So some of these names hopefully are still familiar to some of you. And before I begin, we acknowledge and celebrate the first Australians on whose traditional lands we meet, and pay our respects to the elders past, present, and emerging. So the structure of this talk will begin with a quick introduction on black holes, but it sounds like many of you work on AGN already, so but anyway, I'll go ahead with this introduction, what they are and why we really should care about them. After which I'll discuss the standard AGN paradigm, the evidence in its favor, and also some of the issues that have come up in recent years. Then I'll talk about the spectroscopic sample of high-redshift quasars that our group has obtained, as well as the various methods that we have utilized or developed to better understand the black hole and its radiative output. Along the way, I'll be talking about measuring black hole masses, spins, quasar luminosities, and observed orientation angles, which are all critical quasar properties. Now, as astronomers, I imagine we're all somewhat familiar with what black holes are. The typical colloquial definition in popular science is that black holes are these regions of space-time from which not even light can escape. And that phrase I'm sure you've heard many times. But there's also a much more rigorous mathematical definition of a black hole that is a metric or a particular geometry of space-time, which is also an exact solution to Einstein's field equations of general relativity. And depending on whether the black hole is spinning or charged, we have these 4 exact solutions in this table in the top left, with the most important one being the Kerr metric, which has several critical boundaries as shown on the right diagram. Some of the more interesting features are the ring singularity within the event horizon, and you also have the ergo region, or also called the ergosphere, within the static limit, inside of which geodesics are forced to co-rotate with a black hole, as you can see on the panel on the bottom. Now, not many objects in astronomy that we study have these exact mathematical descriptions in GR, so that makes black holes really quite special and useful as a test for general relativity. Now, according to the no-hair conjecture, stationary black hole solutions to Einstein's field equations are characterized by only 3 externally observable parameters. That is the black hole mass, the angular momentum, and the charge. But typically, an accreting black hole, we think, should neutralize very quickly with the surrounding plasma, so we don't usually think of black holes as being highly charged. Now, one aspect that I want to highlight, because I'm delivering this talk to fellow Australians, is the Carter constant, which I've denoted here as the variable c. This is one of the 4 conserved quantities in the general geodesic motion of any particle in Kerr spacetime. And that's a conserved quantity alongside the magnitude of the 4 velocity, the energy, and the angular momentum. And I want to highlight this because the Carter constant was discovered by Australian theoretical physicist Brendan Carter in 1968, who also invented the concept of tidal disruption events, TDEs, in the 1980s. Now, together with the Carter constant and other conserved quantities of motion, the geodesic motions of particles and photons can be uniquely derived around the curved spacetime. So now that we know what black holes are, I should emphasize that supermassive black holes in the center of galaxies are incredibly important for astrophysics and cosmology. So this image of the radio galaxy Centaurus A shows these incredible large-scale radio and X-ray jets emerging from the galaxy's central region. So it's thought that these nuclear outflows from supermassive black holes play a critical role in heating up the gas in the galaxy, which can suppress or kill star formation of the galaxy. And this effect can be especially potent when the jet axis is 90 degrees misaligned from the rotational axis of the galaxy, which appears to be rare based on available simulation data, but this can happen from dynamically violent galaxy mergers. We can also empirically observe these feedback mechanisms from the coupling of supermassive black hole and host galaxy properties, such as the famous M-sigma relation shown on the right, or the black hole and bulge mass relations. Now, when it comes to higher redshift, quasars are particularly interesting as distant beacons of light because their line of sight can provide information about intervening absorbers, such as the frequency and column density of neutral hydrogen. We can also receive information on metal absorbers, which allows us to study the environment in and around galaxies along the line of sight. Another particularly useful application is the study of the Lyman alpha forest during the epoch of reionization. Some of the work that one of my collaborations has done on these redshift 5.5 quasars seems to show that reionization ends later than we thought, where previously we thought that reionization ends at redshift 6, and now it's maybe 5.5 or 5.3 or something like that. Now, when we look at quasar spectra from many quasars together, one important observation is that the average spectrum of quasars is surprisingly consistent. And this consistency is still present whether we're looking at higher or lower redshift quasars. So this is a key observation, and it should make us as astronomers very excited, because it means that there is a universal mechanism at work in quasar engines, even if we don't yet have a complete understanding of all of the radiative or dissipative processes involved. The relative success of quasar classification models and these generative quasar spectral models using either principal component analysis or machine learning approaches are also due to this consistency. So one clear example of this is the famous black hole images from the Event Horizon Telescope collaboration. Clearly, the M87 star and the Sagittarius A star images look incredibly similar, so much so that you'd be forgiven if you thought that these are both the same image produced by different image reconstruction algorithms on the same data. So part of the reason is that by coincidence, Sagittarius A star is about 3 orders of magnitude closer and also about 3 orders of magnitude less massive, making them appear roughly the same size in the sky. However, because of the smaller size of Sagittarius A star, the day-to-day and hour-to-hour variability is much stronger. So the image is less stable, and what you see here is the time average reconstruction. An exciting application of this quasar consistency is the standardization of quasar sources for cosmology. So some recent work has tried this using the relatively tight empirical X-ray to UV luminosity relation to construct a Hubble diagram for quasars. In the image on the right, you can see the constraints on lambda CDM provided by quasars alone in blue, and the 1 sigma and 2 sigma contours. And you can also see the supernova constraints in orange and red. As you can see, the joint constraints, which are denoted by the black outline, are still fairly wide, so there's still work to be done on the unified quasar model if it is to be useful for cosmology. So the time-honored standard AGN paradigm is essentially this diagram shown here, where the diversity of observable AGN phenomena are all thought to be due to observing AGN at different inclination angles. So you may be familiar that there are different Seyfert types and subtypes, with type 1s having broad lines from the nuclear region, and type 2s having obscured broadline regions. There's also this differentiation between radio loud and radio quiet AGN. The observable evidence for this paradigm includes the study of polarized light, which shows these hidden broad lines. It's also clear from radio and X-ray evidence that the structure of the AGN with its jets aligned with the spin axis and the obscuring torus along the plane is generally consistent with the toy model picture that we have. However, there are some issues with the model, as it's clear that not all type 2s have obscured broadline regions. These are called true Seyfert 2s. Furthermore, some AGN appear to change types, turning on from type 2s to type 1s or turning off from 1s to 2s on relatively short timescales, which is wholly inconsistent with the orientation-based picture. These are called changing look AGN, which are not the focus of my talk today, but members of our group are actively investigating these objects as well. Together with other observational evidence, it's clear that this orientation-based model is incomplete and requires supplementary considerations, such as taking into account the intrinsic properties of the black hole, for example. Therefore, so much of my time has been spent on these constraints on black hole properties, the goal of which is to better understand the diversity of observable characteristics that can arise from black holes with different properties within a particular group of type 1 quasars. The properties that I'll discuss measuring are the black hole mass, the angular momentum, which of course is related to the efficiency by which the accreted mass is converted into light, and also the accretion rate and the observed inclination. To start with, let's take a look at several black hole mass measurement methods that are useful, that are commonly used, and I'll also rank them in roughly in terms of how costly their data is to obtain. Now, the first method that I'll talk about for measuring black hole mass is through these direct dynamical estimates, the clearest application of which is using the Sagittarius A cluster of stars. But one can also apply the same method with ionized gas swirling around the black hole, or even the dust continuum. And for these methods, you would need IFU data cubes. Another method is to use photonization modeling to estimate the radius of the emitting region. And then you would use the velocity broadening of emission lines at various ionization potentials to measure virial motions. For this method, you would need single epoch spectra, making it cheaper to apply than direct dynamical estimates. Now, with reverberation mapping, you'd quantify the time difference between the changes in brightness for different parts of the quasar, such as the continuum and the emission line. This method requires long-term spectroscopic monitoring programs while you're waiting for the stochastic variability. So it's certainly the most expensive method that I have on this list. Now, possibly the most widely applied method is the single epoch estimator, which only requires single epoch spectroscopic observations of broad lines emitted from virialized gas. This method is inherently tied to reverberation mapping because it utilizes an empirical luminosity radius relationship. Now, this method is most widely applied for very large samples, and we also use this method on our data, which I'll describe in the following slides. So our data is based on a sample of quasars with unprecedented completeness, including many new quasars discovered between the redshifts of 3.8 and 5.5. We then select many of the quasars as possible from the brightest faintward for follow-up observations using a variety of optical and near-infrared instruments that I've listed here. We began taking these observations from 2021 onwards, and the result of which is that we end up with a sample of quasars with observed frame, optical and near-infrared spectroscopic data between the redshifts of about 4.5 to 5.3, which have very high completeness on the bright end. We then call this sample XQZ5. So here's our sample in black compared with other similar extruder samples at higher and lower redshifts. So we cover this redshift range between these two other large samples by design, and also compared with XQ100, which is shown in red. Clearly, our completeness on the bright end is much improved. On top of that, because of the high completeness, we're able to capture some incredible outliers with record-breaking unlensed luminosities, including J0529 and J2157 shown here on this plot. One serendipitous discovery which resulted in some media attention is this outlier shown in red called J1144. So here are some example headlines. Aussie scientists discover fastest growing black hole of past 9 billion years. Scientists discover rapidly growing black hole. And my personal favorite, unexpected black hole discovery shocks astronomers. Because amusingly, according to popular media, astronomers are always constantly shocked by or unable to explain their observations. So moving on, what we end up doing with the spectral data is that we fit these velocity broadened spectral lines using a code we developed for this purpose. Combined with an estimate of the radius of the emitting region from the empirical luminosity relationship, radius relationship that I mentioned previously, we can estimate the mass responsible for the central gravitational potential for each quasar in our sample. So the code for this work is publicly available on GitHub, and the sample with its data and measurements will be published soon. So I'll briefly describe the code and how it works because some in the audience might find it useful for their own applications. So this code called PyQSpecFit is first and foremost a spectral modeling code, originally designed for quasar spectra, but it can be used for modeling emission and absorption lines in any object, so long as you change the continuum model. So here I'm showing the data of the magnesium-2 line, which is embedded in a non-trivial quasar continuum. So the model of the continuum includes a power law, a pseudo-continuum, which has the broad iron-2 emission, and also the Balmer continuum model. And the lines themselves are fit with multiple Gaussian components until the residual is minimized. So here we show how the uncertainty of the line properties, specifically the fourth half maximum, responds realistically to the degradation of the spectral quality. So at low signal to noise, even down to a signal to noise ratio of about 5, the measured parameter is still within 1 or 1.5 sigma of the equilibrium solution. Furthermore, it's possible to decompose lines into their broad and narrow components. This is especially important for those that are interested in the broadline region or the narrow line region. So for black hole masses, we need to measure the properties of the virialized broadline region, which means we have to subtract the narrow emission line. Finally, another key feature is the ability to model the host galaxy with a linear combination of galaxy templates. So it's not as sophisticated as specialized packages such as PPXF, but it's a useful tool nevertheless to decompose your spectrum into its galaxy and AGN components. So here are a few of the ways that the code is being used now. Another PhD candidate at Australian National University uses Neelisha Marutha uses the code to study these changing look AGN, which are these peculiar AGN that change types. And another PhD candidate, Songlin Lee, used the code to estimate galaxy chemical abundances and probe fundamental ionized gas physics. In his case, he wants to remove the broadline component to investigate only the narrow lines. And furthermore, in this image, you can observe the simultaneous modeling of a large number of emission lines. So I've used the code myself to take a look at some metallicity sensitive line ratios in the quasar broadline region. And here I'm estimating the chemical abundances in the quasar broadline region for a redshift 6 quasar sample. What we found was that the metallicity in the broadline region at these redshifts is roughly 2 to 3 times supersolar, but only if you account for alpha flows, which can contaminate the metallicity diagnostics. And of course, I also use the code to measure black hole properties, notably the black hole masses using the single epoch method as mentioned previously. Now, in the meantime, we've been working on a complementary theoretical approach to determine the black hole masses as well. To start with, we focus on the quasar SED, the spectral energy distribution, which is made up of many emission components. However, the innermost emission that's most sensitive to the black hole properties is the thermal accretion disk emission, which peaks in the rest frame ultraviolet. So on the right, you can see an example SED of one of the brightest known quasars, where you can clearly see the galaxy contribution in the red end and the peak of the accretion disk in the UV. So we then develop another publicly available code called black hole accretion disk fitting for thermal accretion disk modeling. How it works is that it uses ray-traced multi-temperature blackbody emission from thin and slim accretion disk models. These are all pre-calculated, and the resulting spectra, as you can see in the bottom panels, are sensitive to the black hole properties. So from left to right, you can observe how the synthetic spectra are dependent on the black hole mass, the disk luminosity, the observed orientation, and the black hole spin. After that, we wrap the code around with a Bayesian framework to obtain posterior distributions for these black hole properties. And we take the most probable black hole mass and use the width of the distribution, the marginalized distribution, to estimate the uncertainty. As you can see in the table, we tested a method on this ultraluminous and very massive quasar. The results are very similar compared to the detailed spectral modeling method. Indeed, one can obtain similar results from photometry alone, suggesting that it may be possible to characterize black hole properties without spectra. So going back to this cost line that I showed earlier, accretion disk modeling, which I just showed, can work with broadband photometry, which makes it fairly inexpensive. This method is not entirely new, as shown in this image of Matthew Malcolm's work from 1982, but there have been a large range of improvements in accretion disk modeling since the 1980s, such as including general relativistic effects and calculating the integrated thermal spectra for slim disks rather than thin disks. Now, you might expect that the precision of the method is proportional to how expensive the data is to obtain, but that's not always the case, which I'll now show. So for the ASA meeting talk that happened a couple months ago, I developed this interactive activity using targets taken from the SDSS reverberation mapping project. All of the masses in the panel are compared against fiducial H-beta reverberation mapping masses, which are generally considered to be the most reliable. Originally, I asked people to vote for the panel that they believe is most consistent with H-beta masses. And for the 2 times that I did this experiment during some of my talks, Almost all of the panels received votes, but noticeably numbers 3 and 4 would receive fewer votes, and number 6 would typically receive more. So since this talk is online only, I'll skip straight to the reveal. So number 3 is the masses determined by the photonization method. Number 6 is the reverberation mapping of the magnesium-2 line compared against the H-beta line. Numbers 1 and 5 are single epoch estimators with the H-beta line and the magnesium-2 line respectively. And then number 2 is accretionist modeling, the method in the code that we discussed. So number 4 is just the basic Eddington ratio assumption and luminosity scaling. So the performance of this cheapest method, the accretionist model fitting, fit only to the photometry, appears well, qualitatively comparable to the other methods. And furthermore, only 2 of these methods are not directly coupled to reverberation mapping in some way, and that's numbers 2 and number 6, which are totally independent. So that makes these 2 methods especially valuable because their relative consistency without any sort of rescaling or renormalization tells us that we're measuring a real relationship. So now we spent a lot of time talking about black hole masses. I'll use the rest of the time in this talk to talk about other measurable properties of black holes and what our research has revealed. So the quasar bolometric luminosity, or otherwise the total radiative output, is another fairly important property of quasars. The typical method used in the literature to measure this is based on the mean quasar SEDs from multi-wavelength observations. The result is this static bolometric correction for any observed monochromatic luminosity. What we're finding from our theoretical modeling is that the bolometric correction is going to be dependent on black hole properties, such as the black hole mass or the luminosity. The dotted line on the left shows the static correction from the literature. If anything, this correction is only consistent with lower luminosity AGN and would be an overcorrection for high luminosity quasars. So our findings are in line with this, and we also find that we need an additional correction for anisotropy. So it's clear from synthetic images, these are from general relativistic magnetohydrodynamics simulations, and also synthetic spectra, that the observed orientation angle, while not an intrinsic property of the quasar system, certainly has a significant effect on what we observe. With regards to the question of orientation, I collaborated with another PhD candidate at ANU using data from NASA ATLAS, which is the asteroid terrestrial impact last alert system. Jija found a universal variability structure function once the random walk is standardized by the thermal timescale. Now, apparently there's still some dispersion in the relation, even after the correction, and that's still past the region of the short timescale variability suppression. So we suspected that the dispersion may have something to do with variations in the observed luminosity due to orientation effects, because the observed luminosity informs our thermal timescale. So we tested that hypothesis by assuming a simple carbon-4 blue shift orientation diagnostic. On the left, you can see the same plot as in the previous slide, but it's color-coded by carbon-4 blue shift. So you can see that evidently there's some differentiation there. However, as shown on the right plot, a simple model of the blue shift and inclination relationship shows that these low carbon-4 blue shifts seem to obey the expected relation from the orientation disk model. But these 2 high blue shift points behave entirely differently. So in our 2023 paper, we suggested that the offset of these quasars with strong outflows may represent an entirely different mechanism other than orientation. One possibility is dusty outflows that render the disk underluminous. And finally, but perhaps the most elusive parameter of all, is the black hole spin. We know that the spin affects the black hole's critical radii, and when the spin is high, material can orbit much closer into the black hole than otherwise possible when the spin is low. Therefore, one proposed method of measuring black hole spin is through X-ray reflection spectroscopy, which aims to measure the spin through the gravitational redshift of spectral features originating from material close into the innermost stable circular orbit, such as the strong K-shell emission lines of iron. Now, the strength of the Doppler and gravitational broadening of this line can then be matched to models of the rest frame X-ray reflection spectra convolved with these Doppler and gravitational redshift effects in order to estimate the black hole spin. Another method of measuring the spin is by fitting these thermal continuum models, which is the same method that we've discussed previously, but due to degeneracies in the model, we've been finding that the constraints of the spin are fairly weak, and they rely on having good data or for the data to be well described by these relativistic formalism of the Novikov-Thorne accretion disk models. However, we propose that using the data that we obtained, there is another method to estimate spins by proxy of constraining the radiative efficiency. Now that we have a highly complete sample at a redshift range of 4.5 to 5.3, we can estimate the mass growth rate over cosmic time of the brightest quasars in the early universe. This provides a joint constraint on the duty cycle, the Eddington ratio, and the radiative efficiency. So there are independent methods to constrain the duty cycle and the Eddington ratio. So the goal here is to estimate the black hole spin by proxy of the radiative efficiency at these high redshifts. This could tell us something interesting about the supermassive black hole growth problem. If, for example, we find that these black holes primarily grow through chaotic accretion with these low radiative efficiencies and therefore low spins. So this is ongoing work that will be completed over the following months. Now, before I end, as a quick summary, I discussed today that black holes may be useful for cosmology if only they are standardizable. And for that purpose, I've discussed the efforts we have taken to characterize black holes and high redshift quasars, from determining the black hole masses, the accretion rates, and estimating their observed orientations and spins. This work, which is ongoing, lays the foundation for the development of a main sequence for quasars and a better understanding of the unified AGN paradigm. In the future, we'll extend our theoretical modeling, making better use of developments in accretionist modeling, GRMHD, radiative transfer, and photonization calculations. So thank you everyone for listening, and I'll remain here for any questions and further discussions.
Does anyone in the room have questions? Yes, go ahead.
Nice talk. Thank you very much for this. If you go back to where you compare the methods for calculating the mass, like the plot with the 6 panel. Can you go? This one.
Yep.
Do you have like the chi-square consistency check for this? I would like to see if there is any systematic offsets like for one method, or like does one method underestimate the error or anything like this? Do you have these numbers?
Yeah, I have these numbers, and although I did quantify the dispersion using the median absolute deviation, so from lowest to highest, I think 6 is definitely the tightest relation, and then you have 3, I think, and then so the accretionist modeling is roughly in the middle, with numbers 5 and 4 having the largest spread and 6 and 3 having the tightest dispersion. Does that answer the question?
Yeah, I just see 4 and 5 looks like has more dispersion but doesn't have any systematic offset. But number
yes.
6, it looks like it definitely have some systematics.
Yeah, only 1 and 6.
It's really hard to do chi-square by eye. Yeah,
I think only 1 and 6 have a positive bias, and the others are centered very close to 0. So
thank you.
Yeah, that's from off the top of my head, from what I remember.
Yeah, just to follow that up, apart from the scatter, did any of these methods give, I'm going to use the word better errors here, but I'm not sure what better means in this context, but one of these methods typically give you very large uncertainties, and the other ones give you smaller uncertainties and things like that you could use to distinguish between them as well. Yeah, so a lot of the uncertainties really are building off of the uncertainties that are already present with reverberation mapping, because the single epoch estimators are not totally independent, right? So, I mean, the often stated uncertainty is around 0.5 dex. And as far as we can tell, the accretionist modeling uncertainties are roughly around the same. So yeah, there doesn't seem to be a large benefit in terms of improving on these systematic uncertainties from using this theoretical modeling approach. Okay, cool. Thanks.
Further questions in the room?
Because while we're on this one, if you have low number statistics, then the ones with fewer points will tend to have better correlation. So I was wondering if you took that into account when you were looking at the statistics of which ones were best. Or like, yeah, I guess you could downsample the ones on the left to have the same number as 3 and 6. And then that might help the comparison.
Yeah, that's a fair point. We didn't take that into account for this test. Essentially, I just created this for the purpose of this talk. I haven't written up a sort of more quantitative analysis of these comparisons in a paper, but it's essentially for visualization for this talk.
And I understand that. That's great. I know this is for ECRs. Do any ECRs have questions? Early career researchers, for those who don't know the acronym.
This is a question from a person outside the field, but if we go back to the slide where you showed the different surveys and the redshifts on the x-axis, I was wondering what the y-axis on that plot is representing.
This one?
Yeah, that one. Yeah.
So that's an estimate of the bolometric luminosity based on the Richards 06 static bolometric correction with a 25% anisotropy down correction. So it's essentially supposed to represent an estimated bolometric luminosity, but done in a consistent way between the samples.
The undergrads in the room, do you know what bolometric is? Going to explain bolometric really quickly, just in case.
So the bolometric luminosity is an estimate of the total radiative output of the quasar, just integrating across all the different wavelengths, all of the light that's coming out from the central engine of the quasar.
Thanks.
Very dumb question. You mentioned a bunch of outliers, like the one that shocked all the astronomers and stuff like that.
Yeah, that one.
Yeah, can you tell us something more about these? Like what's happening there? Or do you have any idea of what's happening there?
I'm not sure where the question is heading. I mean, any idea what's happening there? I mean, CE273 is also quite an outlier, and naturally, with the way the quasar luminosity function is, I mean, we tend to find these outliers from these complete samples that we're aiming to obtain. So these quasar atlases that we're doing, and once in a while we find these interesting unlensed outliers. So sorry, I'm not exactly sure where the question is going with.
No, absolutely nowhere. I was just curious about how much you would expect to have these sort of outliers, and if there is if they pose any threat to these universality properties of quasars, or they are just like but if you think they are just some systematics, or I have no idea actually.
Yeah, I think they're consistent with being statistical outliers essentially, and with our complete samples, part of the bonus of doing these quasar atlases is being able to catch these outliers. I could mention that previously these were missed because they were either not in the footprint of other quasar searches, or they were a little bit too low in galactic latitude.
What are the typical errors on these measured quantities? So like the luminosity and the look back time?
So the main error is from the bolometric correction, which is roughly 0.3 dex.
Okay.
Yeah.
Oh, I've got a bit of a random question. Maybe explain this and I missed it, but there was like a picture sort of earlier in the talk where you had like this diagram of like a black hole, and you had like a line saying inner and outer event horizon. I was just wondering what the difference is.
Yes. So with a rotating black hole, normally we think of these Schwarzschild black holes that have one event horizon, and they also have a single singularity as a point-like singularity. But with a rotating black hole, you do end up with multiple horizons essentially, and the singularity also gets spread out into a ring singularity. So these all come from the mathematics of a rotating black hole essentially.
So what does it mean, like, if like the event horizon is like the point where like within which, like if you're at a closer radius you can't escape? What does it mean if you're in between the inner and outer one? Do you know?
So
Not make sense, that question. I have no idea, I'm sorry.
yeah, well, one important effect is this co-rotation with the black hole. That's it's called the lens thirring effect. So the one that you're familiar with is probably the inner event horizon, the boundary from which not even light can escape. But there are interesting effects that occur when within some of these outer horizons or the static limit, such as the lens thirring effect, as I mentioned.
Okay, cool, thanks.
I have one question for you, if no one else has any. Your Pi spec software looks really powerful. I was just wondering whether what happens if you would throw a intermediate type AGN at that software? Can it deal with the kind of very low level broad emission with higher narrow line emission?
Yeah, I mean, so with these changing look AGN that one of our other PhD candidates is working on, he certainly has to contend with a number of intermediate type AGN, and he is currently using the software to work on those. But I think as your concern is probably with this decomposition between the narrow and the broad line. Am I reading into that question correctly?
Yeah, just basically like whether you can disentangle the kind of low level broad line emission. And so like imagine if that broad line component at the bottom was maybe
Much
30%,
weaker.
would you still detect it?
Yeah, it's a combination of many things. I mean, it depends on how well you can constrain the continuum as well. If you have a really good constraint on the continuum and you have weak broadline emission, then yeah, certainly we can detect that with the spectral modeling. The other case is, with the narrow line decomposition, you might expect that there's some degeneracy between, which part, how much of the flux is part of the narrow line, how much of the flux is part of the broad line. And of course, this happens with this code as well. You might run the same code on the same data, but then you'd have a different proportioning of the flux between the narrow and the broad line. But the idea behind the code for our realistic uncertainties, as I mentioned here, is that you would run the code many, many times on a sort of Monte Carlo resampled version of the spectrum. And then each time you'd have a different proportioning of the broad and narrow line. And then you would eventually end up with a measured value with realistic uncertainties. So that's really how we deal with these intermediate types and difficult to constrain broadline and narrow line regions.
That's interesting, thank you. Mark, did you have a question online?
Yes, just a quick follow-up on that last comment that it can be even a little bit more troublesome than that the broad lines of narrow line safe at galaxies can actually be Lorentzian rather than Gaussian, which can actually throw some curveball in there. So you have to, the narrow line safe at galaxies show broad lines, but they are either face on, which would narrow naturally the broad line features if it's in a disk, and or they are just starting up, which would mean that the broadline region hasn't quite built up to the full width that it's going to get. So, but in those cases, you can show that a disk is in fact Lorentzian rather than Gaussian. So that's an extra constraint on that.
Yeah, thanks for that comment. So the code is written in a way where if you really want to, you can change the functional fit. So if you want to change it to a Gauss-Hermite polynomial or a Lorentzian or anything you like, you can do that as well.
Right. Yes. Sorry.
Great talk, Samuel. That was really lovely. Quick question on the Leo's earlier question. I just wanted to make sure I understood correctly. For that outlier, you said that you think that that's just a statistical fluctuation, not something interesting physical, or did I misunderstand your answer there? Like, is there something physical interesting going on here, or is this just a random outlier?
I mean, it's okay, so maybe this, I mean, it is of course something interesting because it is very bright for its redshift, right? So it's still, it is physical in that it is incredibly bright, and it is growing very quickly. It's accreting very quickly. I think it consumes about an Earth mass every second or something like that. Not that it's a statistical measurement error, if that makes sense.
Yeah.
But so
Yeah,
it is a very interesting object, and it's worth a deeper look into some of these host galaxies of these very extreme quasars.
Thanks.
Going back to your BIQ spec fit, like you mentioned that it's less rigorous than PPXF.
Just the host galaxy part, yeah.
Okay, so like, why anyone like should use like BIQ spec over like PPXF? Is it time? Is it realistic error?
So my understanding is PPXF is for this host galaxy and AGN decomposition mainly. Whereas if you wanted a more detailed fit of each individual emission or absorption line, then you would probably want a code package that's more specialized in this line modeling.
So PPXF is mostly modeling stellar continuum, whereas what this can also model the AGN continuum, which PPXF doesn't do naturally.
Yeah.
Whereas the AGN continuum has all of these like very broad features that are quite hard to model. And you would have to kind of separately implement that if you wanted to get rid of that kind of PPXF as well, rather than just your stellar templates.
Thanks.
Any further questions, either on Zoom or in the room? No? Okay, that was a fantastic talk. Thank you so much.
Thank you.
Rossi,
Yeah,
what do we do now?
no, yeah, if you want to have some chat with someone, like individual or in group, I guess we can organize that. Yeah, so some more informal interaction, less informal interaction.
Like now or later?
Today or tomorrow, I think that is a plan depending on someone commitment, like schedules as well.
Okay.
So if you're interested to hear more about research, or if the speaker wants to reach out to any of us, introduce ourselves, if you're interested in any of the research you've heard quickly, you're more than welcome to let Rebecca or myself know, and we can organize small group meetings as well. That's the idea, to follow up from the talk.
Okay, fantastic. Okay, so if you want to talk further, feel free to reach out to us, or we can reach out to you. And if no one else has anything else to say, then we can let you go. And thank you again for that fantastic presentation.
Thank you.
Okay. You are dismissed.
Before you run away,
Oh, yeah, right.
then maybe
Stop recording.
drinks.
Are we gonna stay here?
We can do it in the kitchen.
Yeah, so for those who are still around, we're gonna have some drinks for congratulations.